Hello, all, and welcome to a new chapter. If you did not like the prior chapter, which was on series and sequences, well, I'm sorry, because we're still going to be doing series and sequences, particularly these things called power series, which are going to have, I would say, a different flavor. But as you can see, even on this first page here, we're going to have to work with this series looking stuff still, no matter what the problem is. So kind of getting started, what's the difference between chapter 11 and chapter 10? Well, before we were given a series and we could add up the partial sums, right? We didn't have any variables or functions involved. It was just like, do I have, some we have something like, something easy like 3 to the k from k equals 1. It could be to a certain number or to infinity. And I'd be like, okay, well, I can just plug in those numbers. Really, what we're doing is we're adding a bunch of numbers together. 3 to the 1 plus 3 to the 2 plus 3 to the 3 plus 3 to the 4, which is 81. That's the most I know of powers of 3. And you're just adding those numbers together, and we would ask a question like, oh, do these numbers converge or diverge? In this case, they would clearly converge or diverge here. But that's what they all were. They were just numbers. We would maybe put k's in our notation to have, I guess, a form of a concise way of writing an infinite number of numbers, right? But at the end of the day, it was just adding numbers together. This chapter is like, oh, what if we added x's to the series? Well, what if we create a function out of this? Say, like, let's say an f of x is equal to a summation of, give me 1 second, guys. Sorry, I had to pause this video because someone dropped glass at the house here, so had to make sure to check for that. Okay, so what would happen if we added x's into the series here? And would this even be useful? We can define a function to look something like that, and that's what we're going to be calling as a power series, by the way. A power series is going to be a series that just has x's in it, particularly x's to a k power like this. So if I wrote out the first couple terms, this would be what? Like c1 x minus a plus c2 x minus a squared plus c3 x minus a q plus, let's go one more, like Cn, x minus a to the n, and going on and on forever like that. And this is just like a polynomial, right? Even though it's a long polynomial, it's just like at the end of the day, a bunch of x's, a bunch of powers, a bunch of maybe numbers in the front. Well, we would call these just like coefficient of first term. This would be maybe the coefficient of the nth term. But at the end of the day, we have coefficients, we have numbers, and we have powers, and those are all just what polynomials are. For one, notice that when I say centered at x equals a, centered kind of means like zeroed at x equals a. If I plug in f of a here, right, I'm going to have a minus a, which is 0, a minus a, which is 0, a minus a, which is 0. This all would just equal to 0 at this case. So putting it of this form, x minus a, that means you're centered at 0 here. And this is really long and maybe a little complicated, but at the end of the day, polynomials, this is where this motivation comes from. Why are we even looking at this? Polynomials are easy to calculate, right? I know, and even though we don't do it anymore, we use calculators. If I had something like this, and I knew what these numbers were, say it was like 5, and a was 2, and say this was like 7, and even this was like 1.1, I could calculate this stuff by hand. If I plug in x equals 6 here into something like that. I could plug in 6. 6 minus 2 is 4. When I do it to here, 4 squared is 16, and so on and so forth. And I could figure out what that number is. Other functions, such as trig functions, exponential functions, log functions, inverse trig functions, hyperbolic trig functions, there's so many different types of functions out there, right? But if I look at even something we know, like sine, I say, okay, what's sine of 7? I'm kind of stuck already, right? I don't really know how to figure this out just by hand, just by multiplying, dividing, adding, and subtracting, right? But we can approximate these functions with these power series, which is kind of wild. Is like how is that even gonna like come into play here? That's where complicated functions can be approximated through something called a Taylor polynomial here. So let's create a definition with this. So definition, Pn of x, this is going to be the notation we use, is going to be the summation from k equals 0 to n. So there's only n of them here. We're not doing infinite stuff yet. That's going to be kind of later down the line of a kth derivative. Ooh, a kth derivative as part of this stuff? That's kind of wild. At a over k factorial, and then you have that x minus a to the k here. So this is in above maybe our ck, our coefficient. It's going to change every time I plug in the next k value here. But that is exactly what I wrote right here as well, right? I just put something for that coefficient. And again, we can just calculate this out by just writing it, right? This is what? The first term. Oh, and actually we're starting at 0 here. So it should just be f of a over 0 factorial times x minus a to the 0 power, like that, right? Plus f prime of a over 1 factorial x minus a to the 1 power, right? Plus dot, dot, dot. And that first term is actually a little bit easier to write out here. This is really 0 factorial is 1. X minus a to the 0 power is 1. So this is really f of a plus f prime of a. And because 1 factorial is just 1, I'll just write it f prime of a, x minus a to the 1, plus f prime of a over 2, x minus a to the 2. I'll write one more. Double prime of a over 3 factorial x minus a cubed, and so on and so forth, like so. Because we're going from k equals 0 to n, I'm going to have this terminate, right? And it would just terminate to whatever that nth derivative is, a over n factorial. Let me mix a little bit of room here. X minus a to the n. So if you're comfortable with the series notation and you're comfortable with just having x's be a part of the formula, really we're doing nothing new here. It's just the question, what is this useful for? And I've claimed that this is useful for approximating complicated functions here. So before we get to that, note that it is always going to be a finite series. We wanted to be finite numbers. So like technically, again, even if this is a large string of numbers here, if I plugged in numbers for x and a and so on, I could calculate this just by multiplying, dividing, adding, subtracting. And this is actually what calculators do. They just like looking at power series instead of like actual functions. And something to recall here, we actually have done this already at the very base level in Calc 1. And that's what the section in Calc 1 called linear approximation of a function. That is exactly what this was. I don't know what notation you guys use, but say if you had like uh, the linear approximation of function, we'll say like around some x equals a value. The way you would do that, like the linear approximation function, was the derivative at that value, x minus a, plus the output here. And if you saw the picture of this, say I had a graph that looked something like that, and say this, let's move it around a little more. Actually, I want a better graph. Let's make a graph that's a little bit wider. And let's say that this point was my point A here. My linear approximation would have This same point, the same output at that a, because if I plug in a into this linear approximation function, this cancels to become 0, and my output is f of a, which is still on this graph here. My linear approximation has the same slope at that point, right? And this is how you found your tangent lines. And if you remember, your tangent lines, if you zoom into here, right, your tangent lines looked pretty close to a good approximation around that point you were centered at here. What we're doing in this class, in this section, this chapter, is extending this. Here we only went up to like the first derivative, and note if you were to look at the first two terms of Pn, oh my gosh, that's exactly what we have here. P1 of x is equal to f of a plus f prime of a, x minus a. So we've already done the P1 of x approximation stuff, aka linear approximations in Calc 1. Now we're just going to be building it up to higher derivative stuff here. And notice when I do the derivative of multiple Pn's here, let's just actually do it for one thing here for Pn. They're going to match the derivatives of f of x at that same point you are centered at here. So if I have Pn of x and I look at the first derivative, or actually, let's plug it in at a here, right? Let's not even do derivatives yet. If I plug in a into this function, I'm going to have a minus a, this cancels out, a minus a, this cancels out, a minus a, cancels out all the way through, and I'm left with just f of a. The first derivative of this Taylor polynomial series is, well, I would take the derivative of everything, which notice derivative is just power rule. So I'm going to do the power rule of this, power rule of that, power rule of this. This whole derivative just ends up being a 1 now, right? And then this derivative is 0. Notice how this still gets preserved because I'm still going to have a 1 power for that after I take the derivative of this series here. So when I plug in a, this is still going to cancel. When I plug in a here, this will cancel, this will cancel. This cancels because the derivative of the constant is 0. And I'm left with just the derivative at a when I plug in that here. Same for your double prime. When you take the second derivative, all this cancels because it all ends up being a constant and constanting out the derivative is 0. These get preserved because I take this derivative twice, I'll still have an x minus a to the 1 power. So plugging in a makes this a 0 and 0 and so on. And then this thing, everything will reduce to just being your, ooh, this is supposed to be a double prime. Sorry about that. That's supposed to be a triple prime there. You got to go up a derivative every single time. So sorry about that. I found it in the video though. This term is only going to be the thing remaining when you take the second derivative and plug in a, which means I'll have f double prime of a. This was the same for the triple prime as well, all the way up to the nth prime is equal to the nth prime at a. So your polynomial function, this power series, this Taylor polynomial, which is what we're defining this as, I'm going to call it Taylor polynomials from now on. They match the derivatives of the original function at your point of interest, at the thing you're centered around. And as we saw in Calc 1, when you match your derivative, your first derivative, you were a pretty good approximation here. And it turns out if you keep matching higher and higher derivatives for your functions, and they all match, your approximation gets better and better and better. And we're going to see some technology on that in a second. But let's go to an example for this here first. So let's do the classic thing. I think this is when I did Calc 1, this was like the first example that I was given, right? So full circle teaching it in Calc 2 now. For f of x equals the square root of x, or x to the 1/2, and the thing we're centered around is 4, find the linear and quadratic of polynomials, Taylor polynomials for f of x centered at a. So linear is like linear approximation, so that's when n is equal to 1. Quadratic is like the next step, so n equals 2. So some uh, terminology for us here. So we need to find P1 of x and P2 of x. And it's always going to be the same thing here. P1 of x is up to the first derivative. P2 of x is up to the second derivative here. And our f is different. Our a is 4 now. We can look through this here. So let's just actually go straight with the formula though. So P1 of x is equal to the summation from k equals 0 to 1 of f kth derivative over k factorial times x minus a to the k. Okay, well, when k is equal to 0, the 0th derivative, so this just becomes nothing here. 0 factorial, that's nothing. To the 0 power, that's nothing. So this just becomes f of a, we'll leave it at as x here first. Plus the second term, the first derivative, 1 factorial to the 1 power. So f prime of x, x minus a. Plugging it in there. Okay. Well, what is P1 of 4, right? Because we're looking at a equal to 4 here. So let's plug that in. A equals to 4. P of 4 is going to be the square root. Oh, wait. Sorry. Let me look at this here really quick. Yeah. So I already messed up here. It's not going to be f of x always. There are no, so good thing I saw myself here. There are no x's when you do the power series in your function part. This is all a in the formula here. Your power series should only have x's in this parentheses right here, where you have x minus a. This is an a always like that. Let's confirm. Yes, this has f prime at that a always. So I'm not putting x's there, which is nice for us. This is actually by design and why I kind of like got alarm bells here, because we should be able to figure out this approximation by hand kind of easily here. Because if P1 of 4 is going to be f of 4 plus f prime of 4, 4, or yeah, 4 minus 4 here. Oh, sorry. I'm kind of going off the rails here. Let's like kind of take a step back real quick. Yeah, because I'm not looking to plug anything into my function yet. What I'm looking to do is I'm looking just to literally plug in the values I already know I'm looking for here. I know my a is equal to 4, so for this specific problem, I can simplify what my function is going to be by just plugging in 4 where I need to plug in 4. This is the square root of 4 because my function is the square root function, plus, I don't know my first derivative yet, right? What is f prime of x? That is 1/2 x to the negative 1/2, or 1 over 2 square root of x, right? So f prime of 4 is going to be 1 over 2 square root of 4, or 1 over 4 here. Okay, so this is plus 1 over 4 times x minus 4. Or what is this? 2 plus 1/4 x minus 4. That is my first Taylor series polynomial here. And that's all. I'm just going to leave it at that here. P2 of x is, again, following this function here, the summation from k equals 0 to 2, f of k a over k factorial x minus a to the k, which is equal to the first term plus the second term, which note, we already actually found this in the first problem, plus the third term, double prime of a over 2 x minus a squared. A is equal to 4, so P2 of x is equal to the square root of 4, which was 2. This derivative at 4 is 1/4. X minus 4 plus, I don't know what this is yet. I need to find a second derivative now. So what is f double prime of x? It's negative 1/4 x to the negative 3/2 here. So negative 1/4 x to the 3/2, which means f double prime of 4 is going to be negative 1/4 times 4 to 3/2. So that's getting a little saucy here, but it's something I can do. Square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32. So this is negative 1/32. So I have 1/32 times 1/32 over 2 times your x minus 4 squared. That 1/32 to the 2 here, that just becomes 1/64. Like that. Maybe I'll draw a line connecting to that here so you can make this connection. It's a minus 1/64, like that. Okay, that was the first problem here. And it took a little bit of work, right? We had to do some derivative stuff on the side, but it was something we can find. And even though this does look like a lot here, these are things we can multiply, divide, add, subtract. These are things we know how to do by hand if push came to shove here, right? This would be a lot of work to do. Another thing to notice, your P1 of x is exactly inside your P2 of x, but your P2 of x is just the next term as well. So that's also good to know. What can we do with these? Well, we can use these to approximate the square root of 3.9. So let's see. Let's put a dot here. P1 of 3.9 is plugging that into the function. 2 plus 1/4, 3.9 minus 4 here, right? And at this stage, probably best to get a calculator here. 2 plus 1/4 times 3.9 minus 4. Again, we could figure this out by hand. And actually, for this one, let's see if we can, because that's the point of this, right? To be able to do this without using any heavy duty machinery, right? 2 plus 1/4. This will be a negative 0.1 or a negative 1/10. Or this is 2 minus 1/40, which is 79/40 here. Okay. 79/40, yeah, that does end up equaling 1.975 here. We could long division this if we wanted to, right? That is an approximation of the square root of 3.9. We are approximating this. And the approximation of my first P1 is exactly that. How about P2? That is 3.9. Well, it is P1 plus this term, right? So it's your 79/40 plus negative 1 over 64 of what? 3.9 minus 40, or not 44, 4 squared, 79 over 40 minus 1 over 64. Again, this was negative 1/10 squared. So what does that become? Positive 1 over 100? 1 over 100, like that. And now we're kind of getting to a point where it's like, man, let's just plug this into a calculator, right? Because we can do this, but I'm not going to because we have better things to do today, 1 divided by 64 times 1 divided by 100. And this ended up equaling 1.974. We'll go all the way. 4375 here to my answer. Okay, so it wasn't even that far of a difference, right? These are the same up to 2 decimal places, right? That is how we would do approximating for linear, quadratic, even cubic, things like that. Well, let's compare it to the actual value of 3.9 here. Well, what is the square root of 3.9? Square root 3.9. It's exactly that. So for f of 3.9 is equal to the square root of 3.9, which is equal to, now I don't know how to find the square root of 3.9 off the top of my head, but calculators do. 1.974841765.8, right? Let's compare that to the answers we got. Oh, notice 1.97484. Oh man, it's good up to like 6 decimal places or whatever, like 5 decimal places. And that's only up to P2, right? So like these are pretty good and accurate if you're trying to find approximations for things close to what we already know. And I already know the square root of 4, so it should make sense for that there. In general, there is a way to find like in a remainder term, and that's just like subtracting them, right? Remainder error is, we're going to denote it as a Rn of x. Formally, it's your function minus the power series up to that nth term, right? Minus your Taylor polynomial here. And your absolute error is whatever this is here, absolute here. So the absolute value of the actual answer minus the polynomial approximation answer here. So for this problem, we have absolute error of P1. Let's zoom in here. P1 of x, R1 of, let's actually plug in the number. Absolute value, f of 3.9 minus P1 of 3.9. We know these values, right? P1 of 3.9 was this. F of 3.9 was this, so I can just subtract my answer from 1.975. Oh my goodness. That is 0.000158234. So good up to like 3 or 4 decimal places, 3 decimal places here. Whereas for of the absolute value of P2, R2, 3.9 is equal to, so let's just do this right here, the 1.97484,375 minus second square root of 3.9. That is this minus this. I kind of switched the order there, but that's totally fine. I plugged this into the calculator, as you can see. Oh no, this is I'll write it out. F of 3.9 minus P2, 3.9 is equal to 0 0.1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I can't count. Can't count that many zeros. I'm like kind of getting stuck here. Wait. 1, 2, 3, 4, 5. 5. Golly, dude. That was a little too tough for me. I swear I can count, guys. 1, 2, 3, 4, 5. And then your 1, 9, 8, 4, 2. So again, you can find an absolute error from your values here by just comparing the two values like so. Not too tough. The homework won't be too bad with that. The real thing I'm wanting us to do is being able to find these first or second or third or fourth order Taylor polynomials here. And that's just by finding derivative stuff like so. Okay. We're going to get to like showing the graph version of this in a second, but let's just do one more. So let's approximate ln of 1.5 using P3 of x here, right? Well, for one, what is P3 of x? P3 of x, that's the summation from k equals 0 to 3 of your kth derivative at a, k factorial, x minus a to the kth power. So I can write these terms out plus f prime of a, x minus a, plus f double prime of a over 2 factorial, x minus a squared plus f triple prime of a over 3 factorial, x minus a cubed, like that. And I just remembered now, I totally forgot to say that prior problem is a star problem. So what I want you to do is now use P3 of x to approximate this and compare to the actual value here. It should even be closer than what I got for here, but I gave you P2 of x, find P3, plug in 3.9, approximate the actual value, do the same exact thing I did for P1, P2, just do for P3, and compare to the actual value. Okay, next problem here, back to this. I wrote out what P3 is supposed to be this, but I have a bunch of F's. I have X's, I have A's. How am I supposed to approximate this? Well, what do I need for this problem? I need to know what my function is. To know, I would say need f of x. I need an A. And in particular, I already know what my n is for my Pn, so I might need like an n as well. But here it's like, okay, what is the function I'm looking for? That's not that bad. That's just ln of x. What is the point I'm centering around? Well, if I want to approximate this, I need to choose a point that is close to the thing I want to approximate here, particularly a point that I also know the answer to already. And in this case, the clear answer is a equal to 1 because I know what ln of 1 is. ln of 1 is 0, or we're supposed to know what ln of 1 is, right? So that's going to help us for the problem here. What I like to do also is I like to find all the derivatives first so I can just kind of plug it all in from the get-go. So let's do that on the side here. So I have f of a, in this case, is going to be ln of 1, because a is 1 and f is ln of x. That is going to be 0 here, so I know what that is. F prime of x is, if f of x is ln of x, f prime of x is 1 over x. So f prime of a, or a is 1 here, so I'm just going to keep going to 1 now. F prime of 1 is 1 over 1, or 1. F double prime of x is negative 1 over x squared. F double prime of 1 is going to be negative 1 over 1 squared, or negative 1. And we need our f triple prime of x, which is 2 over x cubed. Yeah. F triple prime of 1 is equal to 2. Okay. So P3 of x is equal to, what is my f of a? 0. Plus, what is my f prime of a? Actually, let me write out this in blue, right? 1 times x minus a is 1 here. Plus f double prime of a, -1. -1 over 2 x minus a squared plus f triple prime of a, 2. 2 over 3 factorial, which is 6 x minus a cubed here. Like that. Okay. We're approximating 1.05 here. So let's plug that in. P3 1.05 is equal to, well, let's actually just go straight to this. This is 0.05. 0.05 minus 1/2 0.05 squared. Oh, I should have done this. -1, -1, right? Because we're plugging in our values of a is equal to 1, f of a is equal to ln of 1, and so on and so forth. That's going to be 0.5 squared plus 1/3 0.5 cubed. So, calculator time. And how about I actually write it down right here? 0.05. 0.05. 0.05. Right? 0.05 minus 1/2 times 0.05 squared plus 1/3. Oh, no, 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 no. Delete, 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 delete. Plus 1/3 times 0.05 cubed. That's going to be a number, and that number in particular is equal to 0.048791667. Booyah. Find the absolute error. So absolute error, remember, is Rn of x is equal to absolute value f of x minus Pn of x. So we're looking for 3, right? Is equal to ln, or let's plug in the value now, right? 1.05 f of 1.05 minus Pn 3 of 1.05. And that is, let's figure this out on the side. F of 1.05 is equal to ln of 1.05, which is equal to 0.487901642. And I can do that by just sub in the calculator as well. I have answer minus that. That is equal to, that's a very good approximation around that point, right? This is its absolute value, so let's leave it as is. 0.00023 4, 5. Man, my dyslexia is bad with that, I guess. 15025. Here. Okay. So that's just for numbers, right? And if I'm looking for an answer, if I'm looking for a problem on my math lab and stuff like that, that's how we would do these problems. However, I think looking at the graphs, really shows you what these things are doing. So let me stop sharing and go to this here. Um, Move that over. I'm sharing the wrong thing again. I already know it. Let's share again. Screens. This screen. Okay, I think we're here. Totally typed in polynomial wrong. I kind of liked this one. I just typed in, literally I typed in like Taylor polynomial visual, and I spelled it wrong, but all these are pretty good for this here. Let's go to Taylor series visualization here. And what this does is you can look at all how all the math looks and stuff like that. Really, the purple graph is your Pn of x's, and I can change the size of my n. I can change where my a is and where I'm centered at, and so on and so forth. This time, right now they have it for sine of x. Let's just do it for ln of x. And I want it to be for a being centered at 1. That was the last problem we had. And we had P3 here. Let me do these steps B1 here. That way I can go straight to P3. Look at what's happening around 1 here. For 1, they equal the exact same value, this purple graph and the red graph, right? And for 2, for P3, they actually, this P3 of x kind of curves around with the red graph for like a little bit. Yeah, it starts to leave after a little bit as well, but it curves a little bit. If I looked at P2 of x or P1 of x like this, yeah, they match at that point still by design, but it's not curving with the graph. And as I increase my n to P2 of x, it curves a little bit more. P3 of x curves a little more. P4, P5, you can just keep on going. And you can even see it at like the bottom part right here. The more I end up going with my P, with my n, the closer it ends up getting to the actual function here. And you can imagine if I did n to be a million, n to be like 100 million or infinity, we might end up just creating the entire first graph here. This is especially the case. Let's go back to 0 here. This is especially the case for other functions like sine of x. I think this one's probably the best one to see what's going on here. Um, let's look at this like that. So this is like the linear approximation that we did in Calc 1. At a equals 0, we can linearly approximate by this straight line. When I go up a little bit, I can start creating a graph that ends up kind of bending along the curve here. And let's just like look at this GIF here. Bam, 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 bam. Look at that. It's kind of like as I go higher or lower in my ends, the higher I go in my ends, my approximation graph ends up bending more and more around the graph we're looking for. This is true no matter which graph we're looking at here. If I have, let's look this again. Yeah. If I have the correct math in here, as I increase my ends, I end up wrapping around my function more of whatever number I'm centered at here. So that's what we should be thinking of when we're thinking of these Pn of x's. Like for Pn3 here, or P4 maybe, it's like, oh, around this 0, I am pretty like spot on along this range around 0. If I did A to B, let's say A was like 7 instead here. Or let's do something like 6. 6 is a better number. Then I start being centered around the A equals 6 value, but the same thing still happens where I end up shifting along or bending along the original graph I want to approximate. Okay, so kind of beat that with a dead horse. Let's move on to more problems that you're going to see in your homework here. Share like that. So more about the remainder stuff. You can always find the remainder by plugging in the actual values you have, right? So that's what we did in this case here. That's how you found what we would call like an absolute error, right? But just like in like a prior section where we're doing of errors of like alternating series, there is a theorem that works for us for how to find a remainder, or at least like a bound for a remainder as well in practice. So just like in the last stuff when we're doing like a bound for the remainder and stuff like that, there's a very similar theorem, and it's called the Taylor's theorem for Taylor's polynomials, and it's particularly in regarding to the remainder because Taylor proved a lot of things about series. Um, and before I maybe like read it out loud here, just remember your Pn of x is equal to, your f of a plus f prime of a, x minus a plus all the way to your f nth prime of a over n factorial x minus a to the nth here. So Taylor's theorem for remainder says if you have continuous derivatives up to the n plus 1 derivative, which actually that's something I've swept under the rug, but you can't do this stuff unless you have derivatives defined up to the amount you want to approximate by. So we need to have continuous amounts of derivatives for these sorts of problems here. On the interval containing x equals a, because we're centered around that a, then the remainder is going to be, actually, oh, I wrote this wrong here. This should be a factorial here. The remainder is going to look like the next term. N plus 1 factorial, x minus a, n. The only difference is your remainder term actually is not an a anymore. It is a c value for some c that is between x and a. So it's not exactly the next term that you didn't put in for your Pn of x. Really, there's like another value that's semi-close because it's between x and a that will be the true remainder. But that's just kind of like dotting your i's and crossing your t's here. Because how do we use a theorem like this? Because we don't know what the c is here. We really don't know. How do we use it? Well, we look for an upper bound for that derivative in that interval from x to a. So say, I have my interval here. Let's say a is the thing I'm centered on. I have like an x value that's like a little bit bigger. There is some c from here to here. Let's maybe draw like purple c. That makes this equation true. That makes your remainder equal to exactly this, where you plug in c to that n plus 1 derivative. However, since I don't know what that c is, and I can't figure out what that c is, figure out the largest value I can plug in this interval here. Then my Rn of x is going to be less than or equal to that largest value, n plus 1 times x minus a to the n plus 1. And this is something I can find. So we need to figure out what is the largest value, the largest c I can plug into my derivative on this interval. And that gives me an upper bound for my remainder, so I don't have to calculate this whole thing, calculate what the actual answer is, like I did here, to find what my remainder is here. And honestly, this is how we would do problems like this in the wild, because oftentimes to find my absolute error, I have to know what the answer is to begin with. And if I know what my answer is to begin with, what's the point of me doing an approximation? It's like, why would I approximate? I already have the answer, right? This allows us to figure out things for functions we don't know. If I don't know how to calculate the function, I can do a polynomial of a certain size. And if I want the remainder, or if I want the error to be small, I can use this theorem to figure out if it's small. Okay, so let's do that for two problems here. Find an expression for the remainder, Rn, for f of x equals e to the negative x, and a is equal to 0. So we have a is equal to 0, f of x is equal to e to the negative x. And I know my remainder term for Rn is going to be the nth derivative of this, whatever that is, and whatever that is. I need to find an expression for this. Well, I don't know what my n is going to be. My n is just a regular thing here. So what are the derivatives here of this? If f of x is e to the x, e to the negative x, this derivative will be negative e to the negative x. The next derivative is going to be, well, we ignore this negative. This derivative becomes, again, pulling out a negative due to chain rule. It's going to be a positive e to the negative x. Third derivative, I know this derivative is easy, negative e to the negative x. Fourth derivative is going to be e to the negative x again. So it looks like my nth derivative is going to be negative 1 to the n e to the negative x. And similarly, n plus 1th derivative is going to be negative 1 to the n plus 1 e to the negative x. So yeah, that looks right here. If I look at that pattern that's going on here. So I can say by theorem, my remainder is going to be less than or equal to and we like to do absolute value stuff here. Like if I know the absolute value of this and the absolute value of that is less than the absolute value of the all the stuff here, like that. But I'll just leave it like that here. So it's less than or equal to the absolute value of your fn plus 1 at some c over n plus 1 factorial times your x minus a to the n plus 1 power here. Would I know what my n plus 1th derivative is? It is negative 1 to the n plus 1 e to the negative c, because we're plugging in c here, over n plus 1 factorial. And I know what my a is in this case, so it's just going to be x, 0. So I have x to the n plus 1 here. Still absolute values for everything as well. Well, because we're doing absolute values, I can maybe get rid of this. And I can say, let m equal the max e to the negative c power, where c is between x and a. Then in particular, I'm just going to have this is equal to e to the negative c, or I'll say it's going to be equal to m, because I've created a new variable, n plus 1 factorial x to the n plus 1. And we're just looking for an expression here, so that's going to be the case for this. If I'm looking to approximate like e to the negative 0.05 or whatever, something like that, then I know what my x is, I know what my a is, I can figure out the c that is the max value between those two numbers, and then I can actually plug in an actual value and get a remainder term. But in this case, it's just looking for an expression. And this would be the flow of how the problem is for a problem like this. We'll do an actual example right here. Use the remainder to find a bound for the error of Pn of x for this, when n is equal to 4 and sine is the function here. So again, what do we have? We have a function, which is sine of x. We have an n, which is equal to 4. We have an a. What is my a in this case? Well, it needs to be something that is close to my value of interest. My value of interest is 0.3. The closest thing to that is 0. And I know what sine of 0 is. Sine of 0 is equal to 0 here, right? Okay. So I can say, by Taylor's theorem, I'll say remainder theorem. My Rn of x is less than or equal to Fn plus 1 x over n plus 1 factorial. It's not an x, it's a c, because I don't know what c is yet. And actually, let me highlight that. That's like the key thing we're going to try and figure out in this problem, or an upper bound at least, plus 1. Here we know we're looking for R4 of x because n is 4 here. So it's less than or equal to the fifth derivative at some c value over 5 factorial x minus, oh, I already know a is 0, so I can just put x to the 5 power like that. And I can say where c is between x and a. X is my value, 0.3, and a is 0. So there's not much my c can be here. If I was to draw this out again, right, I have my 0, which is my a, and I have my 0.3, which is my x, and my c is whatever my max value is along this here. I don't necessarily need to find that. I just want to find an upper bound for this. I need to find a bound for my error, right? Well, let's look at derivative stuff. F of x is equal to sine of x. F prime of x is equal to cosine of x. Let's build up to the fifth derivative. Negative sine of x for the second derivative. The third derivative is equal to negative cosine of x. And my fourth derivative is equal to sine of x again. And my fifth derivative is equal to cosine of x. Okay. If that's my fifth derivative, I can look at theorem. So these are supposed to be equal signs right now. I'm not, this is exactly the case here, but I want to figure out if I can find an upper bound for f to the fifth of c, or an upper bound for cosine of c. Well, I'll say for some m, in particular, we know -1 is less than cosine of x is less than a 1 for all x. That's the range of my cosine function. So f to the fifth of c, absolute value at least, which is cosine of c, is going to be less than or equal to 1 always. So usually you're given a problem where you know a little bit about the function, and since you know enough about the function, you can create a bound for this thing here, which makes life a lot easier for us. I can say, so Rn, or R4 of x, absolute value, is less than or equal to 1. That is from this here, over 5 factorial times x to the fifth. And in particular, I'm looking at an error for sine of 0.3 here. So my x is 0.3, which means I have 0.3 is what I'm plugging in for my remainder. 1 over 5 factorial, 0.3 to the fifth. And I can plug that into a calculator as well. 1 divided by 5 I don't know where I think it's math factorial. Probably could have just done 5 times 4 times 3 times 2 times 1, but whatever. Times zero point 0.3 to the fifth. That is 0.0000225. Why is this important here? This was important to be able to do because I don't know what sine of zero point 0.3 is, right? But I do know I can figure out an approximation for it, and my approximation of P4 of x is going to be within 0.00002 of the actual value. That's pretty cool. Okay, so that was a long video, I know. Please get through it as best you can. Get started on the homework. Good luck on your prior exam, and have a good day. Thanks for watching, everyone.